right, everybody, we're going to go ahead and do kind of the next phase of looking at the half angle formulas and double angle and all of those. We're going to, and actually sum and difference, I guess, a little bit. We're going to deal with some more verify situations. We're looking at now, we're pulling in more than just like a single set of formulas. So we can look back over anything that we've done, double, half, sum and difference, and see if we can show that two expressions are the same. In other words, that their graphs would be identical. They have the same set of solutions for values, and they'll be true for all values of x for their angle measurement. So we're going to do some verify ones first, just to show how we can choose from all of those relationships now. And then we're going to do some, can you recognize what formula is being applied? So that's, again, sort of an application and being able to recognize what some of these things look like. So for this first one, it's really important. This is kind of a new piece in verifying and simplifying. You have to look at your angle measurements and ask yourself, are the angles the same? So are the expression for angles the same? Because if they're not, then we really need to think about making a substitution, because if the angles aren't all x or all theta or whatever, we're not going to be able to simplify them down and make them the same. So if the angle measurements aren't the same, that may be a reason to perform some sort of substitution. And again, we have more angles or relationships to choose from in that case. So when we look at this expression, I see an angle x, and okay, look at this one, it's a 2x. So right away, to me, that's a signal that I'm going to have to do some substitution. So let's see what we can do with that. So we have 2 times tangent of x over here. This expression I'm going to substitute using your formula sheet. That's a double angle formula. That's 2 sine of x times cosine of x. So notice now everything has the angle x, and that's what we're trying to do. If we're trying to verify, we want to show that they're equal. On the bottom, I'm going to go ahead and substitute there too. What's 1 minus sine squared of x equal to? Go way back up to the top of your formula sheet. That's one of those Pythagorean identities. That's equal to cosine squared of x. All right, now let's see if we can simplify this down even more. On this right-hand side, I have a factor of cosine in the numerator, so that's going to give me 2 sine of x over cosine of x. Now you can decide how you want to proceed. Remember our old adage, it doesn't have to be easy, just has to be equal, right? So we could change this side over now, the left-hand side. How do you write a whole number of 2 when you write it as a ratio? Well, remember that's 2 over 1. So just be careful. It's not 2 over 2. That would be 1, which is not 2. So be careful. Tangent is sine over cosine, and we have our expression verified. Otherwise, if you didn't want to change that left-hand side over, you could have just as easily kept the left-hand side and then substituted over here and said, oh, wait, sine over cosine, that's tangent, and then I could have had it verified that way as well. So when we're verifying, we're just showing that those two sides are in fact the same. But here's the new thing to be checking for. Are the angles the same? Are they the same expression? Because if they're not, we're going to have to perform some substitutions. All right, let's try one more of those verifies. So again, let's check those angles. I see a 2x, an x, and an x. So 2 of them are the same, 1 is definitely different. So we have to make a substitution. So what I would be substituting for is this guy right there. Okay, so now look on your formula sheet. You have 3 different options for cosine of twice an angle. One just uses sine, one just uses cosine, and then the other one uses both sine and cosine. So you know you can get there from all of them. Remember these identities, they're just different versions of the same identity. However, remember how some of them are a lot longer and harder to do, and some of them might be a little bit easier. Look at the other side to kind of give you a guide. How would you express tangent squared of x? Well, probably the most common way that people would look at it would be this way, right? Sine squared over cosine squared. So I'm kind of leaning towards having something that has both sine and cosine, because the other side has to end up having sine and cosine in it. And so I'm thinking that I'm probably going to have to use the one that uses both. So that's the choice I'm going to make. Now, when you substitute an expression, do not forget, you need to have parentheses, because I am subtracting everything inside here. So I'm going to use cosine squared minus sine squared of x. And then that's times secant squared. I'm going to go ahead and substitute for that as well. I don't have anything with secants on the other side, so that's 1 over cosine squared. And then I'm going to go ahead and just leave this as sine squared of x over cosine squared of x. Alrighty, now order of operations, we need to be a little bit cautious at how we do this. I see expression on the inside of a parenthesis that I can't do. I see something being multiplied by that parenthesis, so it's going to have to be distributed all the way through. And then I see this 1 minus out front. Following order of operations, I'm going to go ahead and multiply first, then subtract. So I'm going to multiply cosine squared of x. Just think of it over 1 times 1 over cosine squared of x, distributing it through, minus sine squared of x, I guess over 1 times 1 over cosine squared of x. So you can think of it that way if that's the easiest way for you to look at it. Some people maybe would think this whole thing over 1 and just write that whole thing over cosine squared of x. That's fine too if you want to think of it that way. I think this way might be a little bit easier to simplify though if we multiply it separately. So I just distributed to each of the terms on the inside. Cosine squared over cosine squared, well, that's 1. So we have 1 minus parenthesis 1 minus, we got sine squared of x over cosine squared of x. And on the other side, we're hoping we end up with this. Now, if you don't use parentheses, you will get these signs wrong. So this is why it's so critical to make sure you have parentheses. Now that we can distribute through and subtract everything, we did the multiplication. 1 minus 1, that would be 0. So those add to 0. Minus a negative is positive, and you end up with sine squared of x over cosine squared of x, which is exactly what we wanted. So it's really important to remember to distribute those signs. Use parentheses when you substitute. We really need that. Okay, this last piece that I want to talk about is kind of cool. Going back over all the formulas we've done now in 7.3 and 7.4. So all of the double angle, half angle, sum, and difference. And I want to see if you can, when there's numbers in there and they're kind of written out, can you recognize which formula is being applied in each of these? So I'd like you to kind of pause the video each time you do one of these. I want you to hunt on your formula sheet and see if you can find a formula that represents each of these. So let's take a look at the first one and pause the video, see if you can find a formula that looks something like this. Okay, so the formula I think it kind of looks like is the one that looks like this. So if you look at the formula the way it's written out, it sort of looks like that, right? Cosine, cosine, sine, sine. These angles are the same. Those angles are the same. Those are your alpha and beta. What is that a formula for? Well, that's a cosine formula for either a sum or a difference. And you got to be careful. To figure out if it's sum or a difference, you got to look right here. So it's a plus in the cosine formula as though the signs are opposite. So this would be alpha minus beta. That's what that's a formula for. So we can take it a little bit further then. If we know that that's what it's equal to, well, we know what alpha is. Alpha is your 75, right? And then beta is your 15. So this would be the cosine of 75 minus 15. Now, if that's something we can do, which it is, that means it's the same as the cosine of 60. Now, if that's something we can do, I think it most certainly is, cosine of 60 degrees, we can get this all the way down to a half. If we recognize what formula is out there, we can write what that identity is and work backwards. Now, if you would have ended up here with something like, say, cosine of 57, well, couldn't have done anything with that. That's not a special value, but at least you got it down to a single function that we would be able to express. So if it's not a special value, still a better expression to work with, but if it is, we can actually do that. Okay, so I want to do the same kind of thing on this next one. See if you can figure out what formula is being applied. All right, so I'm thinking it looks kind of like this one. What do you think? Kind of a good match? What is that a formula for? Well, that's a formula for tangent of twice an angle, right? Tangent of the double angle formula, and they maybe use thetas, but same idea. So what is our alpha angle that we're looking at? Well, it looks like that's our 30 degrees. So this is a formula for, if I kind of write it on the same side then, tangent of 2 times whatever that alpha number is. And for us, alpha is 30. That's the number that they're using. So that means 2 times 30. That would be a formula for tangent of 60 degrees again. So we have that 60 coming back. And again, if this is a special value, which it is, we can actually do that. We can actually come up with that value, which would be much easier just thinking of it like this instead of doing all that arithmetic, right? And same thing with the last one. I couldn't actually do that arithmetic I started with. I don't know 75. I don't know 15. I don't want to have to go back and use other formulas. I can work backwards sometimes to come up with something that's easier to do. So in this case, tangent of 60, cool. That's square root of 3. But again, if this would have come out to be, say, tangent of 42 or whatever when you did that, well, great. That's not a special value angle, but at least it's written as a single function, a single expression. So we can use these identities, recognize those formulas. Okay, so let's try a couple more. Let's do some that don't have numerical values and see if you can still figure out the formula. So go ahead, pause the video, see what you can do. All right, this one to me looks like sine of an angle times cosine of a different angle minus cosine of that first angle again times sine of that second angle. When I match that up, so sine, cosine, cosine, sine is definitely a formula for sine. Now again, to figure out if it's a sum or a difference formula, we've got to go back to the sign in between, which happens to be subtraction. But now in the sine formula, look back at your formula sheet, the signs are the same. So this would be the sine of alpha minus beta. It's actually the difference formula. Okay, so what's your alpha angle? Well, alpha is the 3x, and your beta is the y. So that means it's sine of the first angle, the alpha, which is our 3x, minus the beta angle, which is the y. Now, those are expressions that you can't put together, right? 3x minus y, those are just two different variables, but we've put it back into a single expression. It's just that one function. So this would be basically the identity part. That's what that expression all expanded would look like if I went back to what that formula was for. All right, let's try one more of those. Pause the video again, see if you can figure out what this is a formula for. So it looks like cosine of the first angle, cosine of the second angle, plus sine of the first angle, sine of the second angle. Now what's confusing about this one is that the first angle happens to be the same in the formula that they're giving you, right? The first angle is just alpha. But instead of the second angle just being beta, they gave you an expression for it. So this alpha minus beta is the second angle in both of them. So what is this a formula for? Cosine, cosine, sine, sine. That's a formula for the cosine of a sum or a difference again. To be able to tell if it's a sum or a difference, go back to the sign in between. In the cosine formulas, if it's a sum for the terms, that means it's a difference in the angles. So it's the first angle minus the second angle. And here's where you got to be really careful. The second angle happens to be alpha minus beta. So do you notice how I put that in there? Alpha minus beta. So it's the first angle minus the second angle, but the second angle is an expression. Why do we care? Once again, back to that whole distribute the negative sign thing. Alpha minus alpha minus a negative plus beta. So what do you have when you put that all together? Well, that would be cosine of just beta. So be super careful when you're doing those substitutions and making sure you understand what the signs of your answers are going to be. So we can do a lot of cool different things when we look at recognizing these formulas and working backwards. So we can verify and we can recognize to help solve and rewrite identities for trigonometric functions.